when we're doing degrees of freedom analysis, when you read through chapter 2.3, they very clearly say that we are calculating degrees of freedom based on the number of equations and the number of variables. But the textbook doesn't really explain exactly kind of in as much detail. If you're going very closely and you highlight, you will find ad hoc definitions of all the different words that they use. So they do say what parameters are, they do say what variables are, they do say what inputs are, what outputs are, and so on. But I have developed this diagram just because I know that students struggle with keeping things straight in their minds when we're talking about the roles of variables. And you'll see in the study guide, there's a bullet point in the study guide which actually specifically relates to this idea of being able to write down model equations and identify the roles that variables take in the model. Now I'm going to switch, and I've developed this. This is a Carl Sandrock specific terminology. It's not a universal terminology. It doesn't 100% map to what the textbook uses, but I have found that I need a bigger word, which I call symbols. So the textbook doesn't talk about symbols, but at a very high level, when we write down model equations, we use symbols, right? And why I like this word is it allows me to refer in a very generic way to all of the different symbols that we write down when we use models. Now, I've drawn T on the side here because even though it is a symbol, we're in almost all cases not going to use it in analysis. In a certain way, we use time to indicate the direction of causality. In other words, things go on this diagram from left to right. And that is kind of also the direction in which time goes. So things that are on the left of this diagram affect things on the right. Now, the big box of symbols, now this is every single symbol that you could give a name. So this is something like a diameter or a height or whatever, right? All of those things are symbols. That big box of symbols is split right up front into things that are constant forever. And forever I'm using here with a little bit of license. Forever in terms of our analysis. In every version of the analysis that we're going to be trying to solve over time. Those things that are constant we call parameters. And even if you're reading the textbook, you'll see that it's important to understand that this is something that we choose. We impose this upon the model equations that we have written down after we have written them down. And so I can give you a set of equations and then give you a paragraph with words. And if the words mention something like, in this situation, in this version of the blending problem, the volume is constant, you identify the volume as a parameter. Later on, when I say in this version of the blending system, the volume is not constant, you do not identify volume as a parameter. And so you shouldn't be thinking about connecting a symbol to a role forever and ever, right? The roles are analysis specific. And so it's because of the way that we've chosen to set up the problem, that we've made the assumptions that we have, we assign those roles. And also very key, there is no way of looking at the model equations themselves. So I can't give you the model equations and have you come away knowing what the roles of variables are. There's one important exception which I'm going to add into this diagram now, but in general, the equations give you no clue about whether things are constant or whether they're changing and so on. There are some loosely used conventions. So sometimes people who are trying to explain the difference between parameters and variables in a model will explicitly put a little bracket t. So they'll say these things are f of t, or they'll be like d of t, just to indicate explicitly that we expect this thing to change as a function of time. But this is conventional. It's not like a rule that you have to follow. I read your models perfectly fine both ways. You'll see the textbook as we move along, because it gets really, really tedious to write lots of t's, right? So it'll start with like being very explicit and putting in little bracket t's on everything that changes over time. And the things that change over time the big split is between these things that don't change over time, called parameters, and these things that do change over time, which are called variables, because they vary. Right? There you go. So there are parameters and variables, and then those parameters and variables get further split up into inputs and outputs. Now, input variables are things that change over time. So most notably, understand that every symbol occupies only one of the way that I've drawn this diagram is that a single symbol cannot be more than one of these things. Right? So up to now, you can't say, oh, this symbol is a parameter and an input. You have to choose. Is it constant over all time, or is it something that could change over time, that is specified over time? Right? So parameters and variables, inputs and outputs. There are no inputs that are also outputs. Now, within inputs, we distinguish between manipulated variables and disturbance variables. I've put manipulated variables in a box here. So again, every input is one of these things. It is either an input, it is either a manipulated variable or a disturbance variable. How do we tell the difference? Disturbance variables are things that happen to us outside of our control. Right? They just happen. Right? If you're trying to control the level of a tank, but for instance, the rain is a disturbance variable. There's no hope for you to stop the rain or take action. You can't sit in the control room and press a button and make it rain, right? It just happens. I've put the manipulated variables in a box because most of the time there are many disturbance variables and few manipulated variables. And so your best strategy is to say, so these are the inputs. Inputs are things that are causally at the beginning of the chain. In other words, they have no cause themselves. They're not caused by some upstream thing, right? But everything else changes because the inputs change. And so outputs are actually what's left. So I recommend that you kind of move from top to bottom, left to right through this diagram when you kind of assigning roles. It's usually the easiest to understand which things will never change or that under our assumptions are not going to change. Almost always these are things like physical measurements of things, like in the cup example, we have all those diameters and the height and so on. Those things are properties of the cup, and as near as we can tell, they are constant and fixed in time. Then we have the things that can change, but are not something that follows from anything. Those are the inputs, manipulated variables and disturbance variables. In the cup experiment, we have neither of those things. So we don't have input variables, and we don't have disturbances unless you're standing outside in the rain. But so we could think of possible disturbances, but as we did the experiment, we do not have a input variable. Everything else, right, is then an output. And in the cup, this would be the volume of the cup, the volume of water in the cup, the height of water in the cup, the rate at which stuff is going out of the cup. All of those things are all output variables. It's confusing to many people, mostly because they struggle to make the distinction between an output variable where it is logical information that is coming out of the system, and output variables where I can draw an arrow with physical material. So in the case of our cup, in the case of the cup, you may imagine that there's something special about F out, right? Because there's actual material coming out of the system. When we do these roles of variables, we are talking about the way that information flows in the system. We are almost never talking about the way that material or energy is flowing. So when we talk about inputs and outputs, a very common wrong thing is to imagine that things that come into the system physically are guaranteed to be logical inputs. So it's common to reason through the arrows on diagrams in terms of material flow to reason about causality. Now I'm priming you for this. This is exactly why some of the TUT problems have been chosen the way that they have. to kind of tease that apart. It is definitely not true. Information can flow upstream in terms of flow rates, for instance, or pressures, right? So I can close a valve downstream and I can have an effect upstream of the valve. That makes sense, right? Because closing the valve will raise the pressure upstream of the valve. So it's not true that inputs and outputs follow the direction of arrows that we draw in material flow. Conventionally, the normal way in which we will be solving equations, we are interested in the simulation problem where the parameters and the inputs are known. And solving the problem or finding the answer of this simulation problem is finding the outputs.